Hi guys, welcome to Learn Electronics Repair. I have here a curve tracer. This is the NI-210SC. I got this from AliExpress, and I got this because a lot of you guys were asking me on various occasions about looking at a curve tracer. So this is a piece of test equipment, a rather unique one to be quite honest. You can build these things, they're usually built as an add-on for an oscilloscope and generally for an analog oscilloscope. Certainly an oscilloscope with a good working XY mode, and a lot of digital scopes don't have that, okay? But this is actually a standalone one, so we'll just power this up. And basically you see what looks like an oscilloscope screen, battery, okay, resistance and frequency. And this is very simple to operate. So you can see by pressing the resistance, I can step through various resistances, okay, from 50 ohms to 7k. By pressing this button, I can step through various frequencies. If I short press this one, it just resets to 1k 500 Hertz and AB. So this actually switches between single or double mode. The little adjustment here, by the way, is for aligning the two traces, okay? So that's how this works. The question is, what do you do with it? Yeah, what is a curve tracer? What use is this? Well, I used these back in the 80s. So when I used them originally, I was working for an electronics company and they had something called a Huntron tracker, which was effectively something a bit like this, but obviously with a CRT then in the 80s, not an LCD display. And the Huntron tracker came with 3 cables. And what it would do is to analyze or display the current voltage curve for various components. Let me show you what I mean. It's probably much easier to show you than tell you in this case. At the moment, I have this in single channel mode A, okay? This comes with meter leads, USB charging cable, which the battery isn't fully charged at the moment, but there's plenty in there. And some crocodile clip leads. That's what it comes with. For the moment, I'm just going to use the multimeter leads. Okay. If you're interested in the add-on curve tracer for the oscilloscope, by the way, I actually built one very cheaply. I'll link the video to this one. This device costs about 90 euros, okay? Let's see if it's that useful in your repair work to be worth its price. Yeah. And we're going to see today how to actually use this in repair work, and then you can decide whether it's worth the cost. There is an instruction sheet, by the way, just the one sheet, and it just tells you how the buttons basically work. It doesn't tell you how to use this, and I'll be honest with you, looking on YouTube, I don't really see any videos explaining how to use these devices. I see plenty of videos tell you how to build one or showing you one, but they don't really go into what you use this for, okay? And that's what I'm going to do today. So the first question, what's the line for on the display? Well, this is plotting a voltage graph. So in the center, this is 0 volts. Okay, this is negative voltage and this is positive voltage. AC. So there's an AC voltage appearing between the two probes. Let's just look at that on the multimeter. So we say, yeah, 3 volts. 3 volts AC. You can't change the voltage. The resistance will change the current that this injects into the device you're testing. Let's go up to 7k. you see a slight reduction in the voltage there, but the higher you set the resistance to, the less current this will inject into the device or circuit board you're testing. I'm just going to set this back to its defaults, okay? And you'll notice that when I put it onto the meter, by the way, you had an ellipse, and the ellipse would depend basically on the setting here. See that? Let's explore what it's actually doing. At the moment, the probes are open circuit, so we can see the voltage. Yeah, I'm going to put it back to defaults, by the way. There you go. We can see the voltage going positive and negative. We could connect an oscilloscope and see what frequency it is, but we don't need to because it tells us there. Okay, and no currents flowing because they're open. What happens when I short them? Well, we get a vertical line. Why is it vertical? Well, because they're shorted now, the voltage between the probes is 0. So this never moves from 0, but the current, AC, is passing positive or negative. And we get a vertical line. Okay? See that? So if we test a resistor, let's say 1K resistor, because that's what this is set to, let's see what happens. We get a diagonal line, and you'll see it's at 45 degrees. That's because the resistance here matches the resistance of the device. Yeah, the impedance of the device. If we put a lower value resistor on there, let's say 100 ohms, well, we should understand it's going to pass more current. It's a low resistance. Yeah, look what we get. We get a line much closer to vertical. My skin resistance practically doesn't affect it. Let's try something like 10K, and we now get a line which is almost horizontal. So it's not giving us a measurement of the resistor, it's just giving us a line at a certain angle. Okay, looks pretty, but what use is that, you might ask? Well, let's look at a few other components. For example, a capacitor. What does it think of the capacitor? What does it do? Well, we see we get an ellipse. We get an ellipse there. Why do we get an ellipse? Well, if you know about capacitors, you will know that the current leads the voltage. That makes sense because when you think about it, you put voltage across a capacitor. Initially, the capacitor is discharged, so it's like a short. So before you see any voltage across the capacitor, you have to put current in first. Current leads voltage, okay? So what we're seeing here is horizontally the voltage going backwards and forwards, vertically the current, and you can see that the capacitor is charging and discharging. So as the current passes one way, charges, and then the other way, it discharges and charges in the opposite direction, and that's what you actually have there. Yeah, looks pretty. Let's try, what's this one? 350 volt, 1 microfarad. Okay, what do we see? Well, we see an ellipse like that now. So because the capacitor is a higher value, and this is an AC signal at 500 hertz, it now can no longer charge the voltage as much. That's why this part of the ellipse here is narrower. The voltage isn't changing so much, but more current is passing through the capacitor in both polarities, both directions, than we had before. So we get more current than voltage, and that's why we get that shape. Okay. How about an inductor? So this is off an old ATX power supply. Let's look at the inductor. And we see similar thing to the capacitor. With an inductor, voltage leads current. So effectively, as you may well know, the inductor, you apply some voltage to it and current doesn't flow initially. It has to charge up the magnetic field, or magnetize basically, and it uses the energy to do that, and once it's charged, more and more current will flow through the inductor. So that's why we get a very similar effect. Okay, let's try a larger inductor like this one. Now we clearly see the ellipse. If we tested both of these inductors on a multimeter, they would just read short. This will tell us it is an inductor, but it isn't very sensitive. Like very low values, a millihenry or something, is not enough to display anything. You need some millihenries, okay? Otherwise you just see a vertical line. You can of course change the frequency, so as we could have done with the capacitor, let's just increase the frequency. The higher the frequency, the more we see an ellipse like that. Okay, let's try a small inductor. So 1 millihenry, what do we have on the highest frequency range? Yeah, we can see it's an inductance, okay. So again, it displays pretty patterns. It gives us ellipses that could be capacitance or inductance, yeah. Doesn't measure them, really. What use is that, you might wonder? Well, let's carry on a little bit. Here's a diode. 1M4007. What's it think of this? I'll put the red lead to the anode, black to the cathode. What happens? Well, look. As the voltage goes negative, the diode doesn't conduct, so there's no current. As it goes positive at a certain point, the diode starts to conduct. We know it's about 0.6 of a volt. And then current passes, yeah? Diode. If we put the diode the other way around, by the way, it'll now look like that. Because this is the positive end now. It looks like that. How about a Schottky diode? Well, same thing, but it turns on or starts to conduct at a much lower voltage, 0.15. Yeah? Zener, well, this is only a 2 volt Zener because this is only giving about 3 volts anyway, so the voltage never goes above about 3. You would expect a Zener higher than a 3 volt Zener just to look like a diode because we never reach the Zener voltage. But let's have a look. So Zener, well, look what we have now. So I'm going with positive here. So in the positive direction, you can see at 0.6 of a volt, the diode starts to conduct. In the negative direction, at around 2 volts, it breaks down. That's the Zener voltage, the NI as it's called, okay? So that's what a Zener will do. Obviously, again, if we reverse the polarity, it'll look that way around. How about transistors? Well, let's have some old ones. So BC107, BC108, but they'll look basically the same. Don't see these much these days, but back in the 70s we all used them, yeah. So BC107, little metal can, NPN transistor. The little metal tab is the emitter, the middle pin is the base. So what do we see? Well, let's go across the collector to emitter. And we don't see anything. Like you wouldn't with a multimeter. Red on the base. Yeah, that's the diode junction that you would normally see on a multimeter. Put the black on the base, so the opposite way around. And we just see the reverse, okay, like we did with the diode. Okay, so NPN transistor. Let's stick with these old ones. So BC158, funny looking things. These are all poles, okay. BC158. This is a PNP. So emitter as one end. I'm actually, let me think about it now. Emitter is this end. But anyway, emitter collector nothing. put the red. So your multimeter would read open because it's a PNP. This shows us a curve like that. Then if we put the black on the base, just shows us in the opposite direction. Okay, so it looks like diodes in there, which is what a transistor would look like based on your multimeter. How about a MOSFET? IFPFZHDO N-channel MOSFET. Okay, what do we have? Anything? Gate. Reads open. Reads open. Drain source. Well, we can see the parasitic diode. And a strange little curve as though it's just starting to switch on. There, okay. P-type, IFPNI-240. Open from the gate. There we see the parasitic diode again, and we see that little curve at the end. You see how it's just starting to turn on. Possibly because my finger is actually connecting to the gate at the same time, so it's getting a little bit of gate drive. Let me just bend that pin out of the way. Let's see what we see now. So I'm no longer touching that. Yeah, we don't see that little curve. So I was basically turning the transistor on, or just starting to, or rather MOSFET on, with my finger putting a bit of voltage on the gate. How about something completely different? So this is a voltage regulator. What is it? 7909, negative 9 volt regulator. What does it look like? Oh, we see something there, something there. Oh, look at those, interesting, yeah. Okay, LED. LED. Well, the LED lights up, and we now get that sort of thing. So, where this was going up, started to conduct, that was about 1.6 volts probably, which is right for red LED and the LED lights, okay? So, depending on your temperament, some of you might think, I could have hours of fun with that. And then others might think, it makes fancy patterns, but so what? Yeah, meh. What use is that? Well, in actual fact, this is a very useful bit of equipment, and I'm going to explain why. And where this is useful is as a comparison tool. So, for example, here we have some IC 74HC32, which we can see is a quad 2 input OR gate. So 1 and 2 are ORed output onto 3, 4 and 5 output onto 6, and so on, okay? And how the tester is useful in this respect is because all of the gates in here should look the same as each other. If we just put one probe onto the negative or ground, so 1 is an input and 2 should look the same, and 3 is an output and it may look the same or it might look different, but all the outputs should look the same as each other. In this case they all look the same anyway. In, out, okay, in, out. So this is a quick and dirty way, you could say, of testing just about any IC, especially if you have another one to compare with. But if it's an IC like this, or an op amp where there's say 4 op amps in one package, all the op amps should look the same as each other in that IC. If one looks different, you can say that is faulty. If they all look the same, you can't 100% say it's okay. But if something looks different on one of the op amps compared to another one, you can say it's faulty, okay? So it's useful for comparison, and also if you just have 2 ICs of the same type. Like these, for example, NI-210SC. These are little switch mode controllers, basically. And we can compare 2 together. So I'll probably just say, I'm kind of guessing, it doesn't really matter exactly where you measure from and to, but they should look the same as each other. And you may get better results using if you know where the ground pin is, for example. So look, this one we can see a little curve like that. If we go to another one, the same, we expect to see the same. Yeah. If we see something drastically different, we can probably say it's faulty. You see, from there to there, that curve, the same sort of curve. So very useful for comparing ICs if you have a known good one. If you don't have a known good one, unless you have some sort of record of what they should look like, it's not so useful to you. So now we find some use, but that isn't the real use for this. In my opinion, and I've used them in the past, and this is how I was taught to use these in the 80s, their real use is for comparing two PCBs, especially if you have one known good one and one bad one. Okay, I know some of you guys swear by these curve tracers, and you may use them in different ways. To me, this I'm going to show you next as the real use for this. But if you're using one for something else, let me know. Let us all know. Yeah. Okay. So PCB comparison. Here we have two amplifiers. Okay. PCBs from audio amplifier, power amplifier. One is good, it works. The other one is faulty. This one with the X on, no audio coming out. I've actually, since initially discovering there was one not working, I have corrected a problem on it, so it may actually be the case now they are both working, but we can still show how to do the comparison. So to do the comparison, first of all, we need double channel mode. So we put this lead here, this one here, and we have two traces, which we're now going to align. Okay, and now we're going to connect the ground leads to ground. It would be nice that they were effectively the same coloured, but I mean that's just an OCD thing. Okay, so ground on this amplifier is here, it's marked ground. Okay, so ground, and the other one ground. So we're connecting both grounds to here. Okay, if we short the lead now, well, you can see this one is on a short, this one isn't, and you see one vertical line and one horizontal line. Put them both together onto ground, two vertical lines. Yeah, so we're looking at both boards at the same time. Let's see if we can see any differences. So let's just start around here. This is an op amp. Which one is it? TL071. Okay, we can't say what we should see, but what we can say is we should see the same on both. If we don't see the same on both, there's a fault in that area, the circuit somewhere. Okay, so pin 1, they're both the same. They're both the same. Pin 2, both the same. Both the same. Both the same. I mean, there may be slight differences, but you have to decide if it's within what you'd expect. Both the same. There. So you see, we have a clear difference between both PCBs here. Yeah. Clear difference. This pin, same. Definitely different. This one is almost like a short-ish type thing. This one is like a completely different type thing. Okay. Next one. Again, they're somewhat different. This one. the same. So we know there's some major difference between the two on this chip. This could be a faulty chip, this could be something connected to that pin, but this is telling us to investigate that. Okay, let's look at this one. So same, 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 here, same. This one is completely different also. So this is the faulty board, which is reading like a short again compared to the other one here. Similar-ish, both the same. So if you go around the various transistors and IC pins, anywhere really you feel like you're looking for differences, these things. So what do we have there? Same, 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 both the same. Do you see now why this is such a useful bit of kit? All that was the same in that area. It's telling me there's something very different between the two around here. So we know this is pin, let's see which pin is it. TL071 again, pin 7. So if we find the data sheet, dual op amp, FET input. Yeah, so that is the VCC pin. So it's telling us on one of the amplifiers there's a short or near short between VCC, which is probably a 15 volt supply on this amplifier, and ground. Okay, could you find that with a multimeter? Of course you could. In fact, let's check this out. So this is the pin 7, this is the faulty one. I'm on continuity mode, it doesn't bleep, it reads 121. Yeah, so it doesn't bleep. 121 ohms. Compare that with the good one. That reads open. So it's not a short, it's just a low resistance. I mean, a lot lower than it should be. How about diode mode? Well, the good one, which we're already on, reads 1.89. Okay, and the bad one, 0.092, so much lower. So yes, there is obviously something there which we can see with the multimeter, but personally I believe using the curve tracer to find the problem, because you're just going through both boards together and looking for anything that's different, and it's obvious when it's different, I think you're more likely to find the fault using the curve tracer, even if you then change to a multimeter to investigate further. So what I would do with this now is figure out where the 15 volt comes from. Well, it's not external to this board, I know that. This only has plus and minus 50 or 60 or something. I think it's 70 actually, and ground. So there's going to be some voltage regulators on here somewhere generating that plus and minus 15, I would say. But I have a direction to go now. So guys, that's how you use a curve tracer, and hopefully now you're thinking it's not just a toy that makes fancy patterns, it's actually another very useful tool. And when it comes to fault finding, the more tools you have, the better. And some tools are better for use in some situations than others. You will not find one tool that suits every scenario, but there are some scenarios, this is a very good example, where that is an extremely useful bit of kit. in my opinion. And that's how I was taught to use the granddaddy of this, the Huntron tracker, back in the early 80s. Okay, so I'll put the link in the video description. I still have the coupons from AliExpress. These ones run out, by the way, at the end of July, but I already have another set of coupons that will take you into mid-September. I'll announce them as soon as the other ones run out and they activate. Okay, so yeah, you can save some money as well. Let me know what you think. Yeah. Do you already have one? Is this something you've thought about buying? Is this something you've never really seen before? Or is this something that you knew about but didn't really know if it's any use to you? Yeah, all of those things, let me know down there. Okay, hope you enjoyed that. Thanks for watching, and I look forward to seeing you all soon on Learning Electronics Repair. Ciao for now, guys.